Thanks, David. I am so excited to be kicking off our session today, and I am absolutely delighted to talk to you guys today about Tactum, a skin-centric approach to digital design and fabrication. My name is Madeline Gannon. I am a PhD candidate at Carnegie Mellon University, and I also head madlab.cc, a design collective working at the intersection of architecture, robotics, and interaction. And I had the good fortune of working with the user interface group at AUTODESK Research to develop Tactum, and I just want to convey my gratitude to the two co-authors on this paper, Tovi Grossman and George Fitzmaurice, for all of their support throughout the development of the research. So what is skin-centric design? Well, we should probably start with how do we design for the body? The body is an extremely complex surface for digital design, especially when it comes to wearables. The contours and curvatures and non-Euclidean nature of our body makes it particularly difficult to use conventional CAD software. This software tends to ignore the body, and it pretty much ignores the body, and there's a lot of guesswork that designers have to do for how this thing is actually going to come in contact with the skin. So even really sophisticated designers, like this one who just had her fully 3D printed dress acquired by the Museum of Modern Art, she has to resort to using virtual mannequins in order to test out the fit and finish of her designs. So what if we were just to remove all this guesswork and just design on the body? Skin-centric design, then, is a series of strategies to leverage your skin as an interactive canvas for creating 3D printed wearables. So the work of two main communities is what's making skin-centric design a viable approach for creating printed wearables. The first community, really within the last 5 years, and probably particularly familiar for you, is the HCI community working with skin input for mobile computing. So the past 5 years, they've seen incredible innovations related to hardware, related to software, related to research in the physiological and social response to how skin input can be a mode of computing. And there are a number of really great affordances that we can appropriate from mobile computing and adapt it to computer-aided design and fabrication. So, for example, the idea that skin-based interfaces are always available, that they inherently provide tactile feedback and multidimensional input, those are all really great tools that we can begin to translate over to 3D modeling on the body. The other community, also coincidentally within the past 5 years, is the design community. There's been a generation of designers who are no longer using 3D printing as a rapid prototyping means. They're using it to create real products that go on real people and that also solve real problems. So whether it's how we make a rigid material flexible and soft, or how we give identity to people who are wearing these prints every day of their life, these designers are sort of paving the way for this technology to come into our home and come into our everyday life. So skin-centric design seeks to bridge these two communities and find a more compelling way for 3D printing to integrate into our everyday life. So in our paper, we looked at multiple points of views, multiple configurations, and domain spaces that could be applicable for these design tools. And you can begin to think about these in terms of either the hardware and sensing that you use, or the interface configurations that you want, or even the types or numbers of users that are in your system. And doing a quick survey of the body, we can see that there are a number of artifacts that are sort of ready for skin-centric systems to design. So your head and your face, for example, those are things like eyewear, wearable electronics, or protective headgear that all can be designed on your skin. Legs and feet, medical braces, athletic gear, or shoes, these are all things, although fairly hard to reach, these are all things that we can have sort of bodily input to create and model. With the design considerations that we outlined in the paper, we created our own prototype system, Tactum, a skin-based modeling-to-fabrication tool that lets you it captures your tactile interactions with your skin. It translates that for you to a CAD backend that you don't see, and it creates geometry that's automatically ready to fabricate. And because we put this on our body, or we build the geometry from our body, it's naturally designed to actually fit, so we don't have to do any of this sort of trial and error of normal CAD tools. So to get from your body to digital geometry to physical print, we do a number of things on the gesture recognition and tracking side. So we first created 3D skeletal data of the hand and arms, both of them. We can then begin to isolate the forearm and develop base geometry that then we can add interactive, dynamic geometry that connects to your touch-based input. So in our initial prototype, we decided to use one sensor and to focus on the forearm. In this configuration, we're using a Connect V1. And we're doing our touch detection by adapting Andy Wilson's depth camera's touch sensor to the geometry of the arm. So we sort of simplify the geometry of the forearm and create 2 touch volumes that track and move with your arm as you're moving around the workspace. When your finger sort of goes into that volume, we know we have a touch. And from that sort of simple process, and by tracking the acceleration and the frequency of touch with that one sort of low-resolution sensor, we can extract a number of gestures that we can then send to a virtual modeling environment to drive our interactive geometry. So with Tactum, we sort of take an alternative approach to conventional CAD systems. We don't build geometry from points, lines, planes, surfaces, that sort of thing. What we do is we create animate form that's then stimulated by our gesture. So we explore this idea through 3 modes. Direct manipulation, where your gesture begins to directly change the geometry of around the forearm. This gives you the most amount of freedom with what you do, but at the least amount of control over the actual geometry. So although you're impacting the form, it's often like traditional CAD modeling tools, very sculptural. With this demo, we then subtract the form from the volume of the forearm, and we get this cylindrical ABS-printed armlet. There's also parametric manipulation. In this, you have more control. The form is more controlled. Your gestures modify the open parameters of an already existing animate-based geometry. So here, for example, we're pinching and touching and scrolling and manipulating this pink caterpillar form that gets printed out. This is printed on a object Connex printer with a multi-material, so it's a soft, squishy rubber. Kind of emulates the actual geometry. Lastly, generative. And in this mode, your gestures, they don't modify the geometry. They modify the underlying algorithm that the geometry is generated on top of. So here, for example, we're creating a heat map of touch, and that is being sent to an agent-based modeling system that generates sort of extra structure where you touch. So on the left, you see a 3D printed, speculatively, a 3D printed brace. So the idea is that where you touch more is where you might need more support, and you can generate extra structure towards that area. So the combination of the touch sensing and touch tracking, as well as this sort of intelligent geometry, really strikes a balance between intuitive gesture and imprecise input and very precise designs. So I thought I'd walk through a demo on this one. I'm using my very, very imprecise gesture to design a smartwatch that fits a Moto 360 band. So I have a spring system generated on my arm. I'm tracking my hand movement, and I can set a repulsion point that can be the size of a particular device. I can begin to pinch to test out how I want this thing, and then touch to lock it in place. And then I can bring a physical object and put it right on my body and begin to tweak the design to make sure that we have an adequate fit. And then we can 3D print the thing right away. Tactum doesn't generate geometry that can't be printed, so we don't have to do any post-processing. And we can just pop it in and go. So some takeaways from this. Taking a skin-centric approach to 3D printed wearables can ensure an ergonomic fit and printability by embedding the intelligence of our machine systems into the actual geometry that we're using. By building geometry off of the body instead of in sort of blank Euclidean space, we can craft something that is attuned to our specific contours. This is an opportunity to open up these design systems for end users to customize and personalize goods and products. And we can have an experience that's as personal as one's body with that. And I'm particularly excited for areas of future work. So, for example, we focus specifically on the forearm, but other parts of the body would be incredibly interesting and challenging to do. For example, full body pieces where you have to reach all around, or hard to reach places like on your feet, for example, might be quite interesting. Using multiple sensors, we decided to stick with one sensor just to sort of push the limits of what we could actually detect and use in our gesture to modeling system. Designing for joints in motion. Well, one of the benefits of using the forearm is that we sort of avoid the dynamic stresses of our joints. But if this were to be used for medical braces, that could be something that could be really taken advantage of and explored deeper. And to explore deeper exploration of medical applications. I think this is really exciting for the idea of at-home therapy and recovery. And lastly, and probably the most odd, is multi-user systems. So how could you, like as if you go to a tailor, how could you have someone design something on you? What are the social implications of that, and what are the social constructs that we can create through them? Thank you, guys.
We have some time, like 5 minutes, for questions. Please step up to the microphones and, yeah.
Hi, I'm Mira Donchev, Adobe Research. Really nice work. Can you talk a little bit about how the person puts this beautiful bracelet on or off? Because it seems like that's an important consideration that has, ties to materials and whether they're stretchy or not.
Yeah, a lot of this sort of leverages my experience as a designer. So I create something that I'm pretty sure I know is going to fit. So with these guys, I made sure to use a nylon, a laser-sintered nylon that is both rigid and flexible. These are basically really thin filaments, about 2 millimeters. So it has a sort of flexibility to sort of stretch around the body and stay on the body. The clasp system is just a sort of half lap that sticks together. So it's very, very simple.
Okay, thank you.
Thank you.
Questions? I have a question. Have you considered using tools like brushes or even marking directly with a non-permanent hand on the skin?
Yes, I'm very excited about that, actually. I think that might be a great way to mediate multiple user systems. So, for example, if you're at a doctor's office, maybe there's a pointing device to sort of take off the social anxiety of someone touching your skin in a socially awkward way. But yeah, actually having real input, I was playing with that with actual projection. So you paint a bit on your skin with one demo.
Thank you. Please give a hand to Madeline.